Thank you. So I'm going to talk about some of my laboratory experiments using a simulated lunar environment on minerals and mixtures in the mid-infrared. So I'm doing mid-infrared emission spectroscopy and trying to understand the differences that we get between terrestrial and lunar environment. Where? Okay, sorry. Okay, so some motivation and goals for this project are that, as talked about in the previous talk, the surface environment is much different than that of the Earth. And because of this, we can, and the way the spectroscopy works, in that we are comparing to a spectral library. If we have data from an airless body like the moon, and we're comparing it to terrestrial spectral library, they're not going to be exactly the same. We might not be able to make a direct comparison. So I'm going to be talking about using the thermal gradient and trying to interpret how that affects our spectra, as well as how grain size affects our spectra. And hopefully this will lead to creating some non-terrestrial spectral libraries, and that will help our interpretation of data. Okay, so thermal gradient. Last talk had a much better pictograph than mine is, but just to show you, for the lunar surface, we have the sun coming in, heating up the surface, but since there's pretty much no atmosphere and we're exposed to the cold vacuum of space, the very top layer is much colder. And when we're using instruments like a diviner for our mid-infrared radiometer, we're sensing through the top layers, and all the grains may not be at the same temperature. And so you can see that comparison. This is from Henderson and Joukowsky, Earth and Mars thermal gradients within the top few microns. The moon has a much more extreme gradient. Okay, and since diviner is sensing multiple temperatures, this is going to affect our spectra. So just a quick introduction, hopefully, if you're not so familiar with mid-infrared emission spectroscopy. This is what a spectrum looks like. This is anorthite. So we have a wave number, sorry, not wavelength, on the X, and emissivity on the Y. Some of the main features that I'm examining are the Christianson feature, which is shown here in red. This is our peak. This helps us tell what silica or silicate we're looking at, and this is especially important for diviner because they have bands concentrated around this peak to try to identify what composition we're looking at. Other important features are Rastron bands, shown here in purple. These have to do with your bonds, and then your transparency features shown in blue, and these are due to volume scattering. So overall, this gives us a great spectral fingerprint for the mineral we're looking at. So how do I simulate the lunar environment while still on Earth? This is PARSEC, the Planetary and Asteroid Regolith Spectroscopy Environmental Chamber, housed at Stony Brook. And it's basically this box. So we have it hooked up to our nuclei FTIR and a vacuum pump, so we can get down to about 10 to the minus 6 millibar. And we have a solar lamp to try to simulate solar radiation you might get on the surface. And then when we look inside the guts of PARSEC, we can see we have a dewar in the back. We're doing liquid nitrogen cooling. As the sample wheel, I can load up to 6 samples at a time, and then heat from below so that we can really try to get that gradient in our samples. Okay, so for the methods, I'm using pure samples, pure mineral samples, as well as some mineral mixtures. And these have all been ground and sieved into different particle sizes. Here I'm going to concentrate on augite and anorthite because those are what I've used in my mixtures. And also quartz. So adding quartz to equal parts augite and anorthite, and seeing how that affects our spectra as well. I've chosen these kind of to try to look at a Nordic type of composition we might see on the moon, as well as some of the highly silicic spots that have been identified. Okay, so this is the first of many plots you will see. We have a terrestrial environment spectrum of, again, anorthite in black, and then in the lunar simulated lunar environment in blue. And some of the main differences that you see between the two are in the Christiansson peak. It's about a 50 wave number, 0.3 micron shift. And this is a pretty big shift, even though it may seem small. When we're looking with Diviner at the Christiansson peak, this could change our interpretation from anorthite to something that's more like a quartz sample. What else? The other thing that you see is that the Restron bands and the other features have all a much lower emissivity under the lunar environment. So looking into grain size variation, this is anorthite and this is under the simulated lunar environment. The CF shown up here, we have very little variation, which is good. We've already shifted into the lunar environment from terrestrial, so minimal grain size variation is nice. But the Restron bands, again, we're even getting more of a shift between grain size, which you do see that in terrestrial spectra as well. But the trend we see here is more that a smaller grain size has lower emissivity values. And that's kind of the opposite trend that we see in Earth spectra. You also see transmission features starting to show up in the smallest grain size fraction. So moving to the other pure mineral, augite, again, we are seeing the CF here. This does show some variation. And so, we're just compounding on the differences that we get between our terrestrial and the lunar spectra. And this is a bit worrisome because we don't expect a grain size to have an effect on your Christiansson peak. And with other minerals, I've looked at Diviner resolution and seen that this is something that you would be able to detect with Diviner. Other than that, there's Strahlen band features. They show a similar trend, though the smallest size fraction is going against that grain, but less of a strong difference. And then the transparency features in the small size fraction. So going into the mixtures of the two. Here again, Christiansson feature, we have the pure end member of anorthite in green, if you can see that, and augite in purple. And you see the CF shifting between the two, and you see the other features kind of, again, shifting between the two in concert with the proportions of each mineral. So I want you to notice the shape of these in the terrestrial environment. Now, when we go to the lunar environment, it looks much different. And again, we see the shift between the end members, purple for anorthite and green for augite, but the Restron bands are showing much more spectral contrast, and it seems that as you get closer to anorthite, you go down in your emissivity, so you're increasing your spectral contrast. And even at 50% augite, you're really seeing the augite features showing up more strongly than the anorthite features. Okay, so just to summarize the two-component mixture, and to look at the CF trend, which again we would be noticing most in Diviner, we have pretty linear trends for both of terrestrial and simulated lunar environment. Now, when we add a third component, we add quartz. This is terrestrial data. Here, quartz, our pure quartz is in blue, and a 50-50 augite anorthite is in black. See the CF shifting between the two. But what's interesting here is that the quartz Restron band features, this nice doublet, really starts to show up at only 20% quartz added to the mixture. And when you go into a simulated lunar environment, again, the whole of the spectrum looks different, but you do see that doublet kind of showing up at 20% quartz, and the CF shifting between the two end members of black as 100% quartz and red as the 50-50 mixture. So again, to look at those together. The CF is shifting. It's nonlinear here. Though if you think about that 20% quartz seeming to kind of dominate the spectra, you could argue that there's a linear shift trend between these and pre-quartz domination of the spectrum. And just to kind of summarize, we have fairly large shifts between terrestrial and lunar spectra. We're starting to see some shifts even with particle size under a simulated lunar environment. When we look at the two-component mixture of Ajite anorthite, we see fairly linear trends in our CF shifts, but the Rastral bands and the overall contrast shows much different trends that we expect on Earth. That can be applied to the quartz mixtures as well, with small amounts of quartz, only 20% showing up within our data. And I mean, the main takeaway point here is that they're not the same. And if we want to be able to directly compare, we're going to have to do a lot more of these types of experiments. So that's what I'm going to continue working on, looking at other minerals, other mixtures, trying to downsample these again to diviner resolution to see how well they show up in our data, and actually looking at some diviner data, and then hopefully looking at some lunar soil samples that we're supposed to get hopefully soon in the future. Thank you.
Do we have any questions for this last speaker? Excellent.
I'm Clark. So when you say simulated lunar environment, are you also working with samples that are simulated for the actual physical characteristics of lunar soil? So what are you using for your what are you using for your lunar soil, basically?
So right now I am working with just these pure mineral samples to kind of build up the base, and in mixtures I have looked at JSC1A and seen a similar kind of shift between terrestrial and simulated lunar environment spectra for that simulant. However, I have not been able to sieve those out yet into different sizes.
The physical characteristics are so different that the surface geomorphology, that'll produce other differences as well. But it's interesting that you see that difference just from an environment, just from the environment.
Yes.
So basically it's low gravity and temperature simulation, is it?
Yes, yes.
Okay.
Well, we don't have low gravity, sorry.
Okay, so it's just temperature.
It's just the thermal gradient, and
okay.
Yeah, we don't have a capability of doing gravity.
Okay,
here.
thank you.
I'm sorry.
Yeah, could you, maybe you said this earlier in your setup, and I didn't catch it. The solar illumination is critical here, obviously, and that was something I know that Carrie Donaldson worked on carefully, and the only way she could determine the amount of solar irradiation was basically to look at the lunar samples and to adjust it until you got the same answer. When you have your experiments, how have you constrained the amount of solar illumination to mimic the lunar environment?
So right now we don't have that capability, but we're hoping to improve our setup to get that capability. I'm working with Carrie on trying to figure that out, actually.
Okay.
Yes.
Yeah, because that may help answer some of the issues that you've raised.
I mean, the strong spectral contrast, that's definitely something that is dependent on solar illumination, and I know Carrie has looked at that a lot.
Right.
So and especially looking at actual lunar samples, it's much less.
Yeah.
So yeah.
Okay.
Thanks. Final applause for